Okay, very good. So in the last session and a half, let's say, we kind of covered basics of electricity and resistors, capacitors, and inductors. And that was all to sort of build the basis here for looking at a switch mode power converter and what it does, kind of how it operates, and that'll give us the basis for, how do we convert AC to DC power, or even DC to DC or AC to AC power with our systems. So to start, this is all review stuff from the last the last sessions. So we have the very basic resistance. Resistance is the property of resisting a current flow due to an applied voltage. That's the easiest way to think of a resistance. Ohm's law here defines resistance in ohms as volts over amps, or voltage divided by current. And just as a reminder, the power loss in a resistor can be found, the fundamental equation is power is voltage times current. But that can be arranged with Ohm's law here to see the power in a resistor is proportional to the square of the voltage over the resistance, or the square of the current times the resistance. You'll see these terms in sort of some simple equations as we get into AC power and other things later. So remember, a capacitance is the property of a component resisting a change in voltage due to a change in current. So you apply, and that's defined by this equation here. You apply a current, and that drives a change in voltage. Whereas with a resistor, you apply a voltage or a current, and you directly get the other. It's directly proportional. There's no dynamics to this equation. A capacitor, you apply a current, you get a change in voltage. And then when that's transformed to the frequency domain and you look at reactance, you get this complex number. And this reactance is also measured in ohms. It's just understood to be complex, frequency dependent. Inductance is the property of resisting a change in current due to an applied voltage. So inductance and capacitance are analogs to each other. So with an inductor, you apply a voltage and get a change in current, whereas capacitors were the other way. And C and L are the capacitance and inductance of the component, respectively. So that gives a magnitude of how much of a change you get when applying voltage or current. The reactance of the inductor, again, is this complex number. Just note, again, it's an analog. 1 j omega L versus 1 over j omega C. They're just reciprocals of each other. And we did talk about some basic low-pass filter concepts last time. And what we had was an RC low-pass filter. In green is this guy that I didn't put any axes on here. This is frequency in hertz along the x-axis, and this is a magnitude of the transfer function, h as a general thing. So at these low-pass filters pass signals at low frequency. There's no attenuation. That's what 0 means on this scale. I really shouldn't have introduced decibels just now, but too bad. 0 means no change in the signal. A positive number means it's amplified. A negative number means it's attenuated. So no change at low frequencies. And the RC filter comes down here with a corner frequency of, this is 100 hertz, starts to roll off and attenuate high frequency signals. The LC made out of a capacitor and inductor low-pass filter is the blue line. And while he still passes everything at low frequency, when it gets to this 100 hertz corner frequency, that's where we see the resonant peak we discussed last time. That all comes back to these reactances canceling at a certain frequency. And then the LC filter attenuates high frequency components and actually does so better than the RC filter. So you can see it's rolling off faster than the RC filter. So that's the background to talk about everything else today. Oops. So starting with an ideal switch, we would recommend represent this schematically as just a switch. And if you want, you can draw in a little control terminal here. We would define the voltage across the switch this way. Oops. So the switch and the current through the switch that way. And that's the same as we've been defining, that's the same convention we've been using for other devices. Voltage across and current through have this kind of relationship. So that's the ideal switch there. The ideal switch, when it is open, like shown, can block voltage in either direction. So if a positive voltage is applied to it or a negative voltage is applied, it will prevent any current flow. You can think of it as when the switch is open, it is an infinitely large resistance. Zero current will flow with any voltage applied, either direction. When it is closed, I should have provided these. When the switch is closed, it can conduct an infinite amount of current in either direction. So when the switch is closed, you can then think of the switch as a resistor with zero resistance or very small resistance. When it switches on and off, it does so in 0 time. It takes no time to switch. You send the signal, it's closed. Is fully controlled, meaning the open or closed state of the switch is only controlled by this, we'll just call it the gate. It'll make life easier later if we call this the gate of the switch. So fully controlled means only the gate decides whether the switch is open or closed. And this kind of falls out of what I've already said, that the ideal switch is lossless. That when current is flowing through it, you don't have to pay, you don't end up with any of these I squared R losses when current is flowing in the device. You don't end up with any V squared over R losses when the device is off. And a little more subtly, this switching on and off in 0 time results in lossless switching for the device. All right, so that's the unideal switch. We'll talk about what we're going to do with it. So a common problem for converting power is that you want to take a high voltage and convert it into a low voltage for some other things. You might have a 12-volt car battery and you want to give 5 volts to your USB port, something like that. In fact, that's a fine example. Maybe I'll use it. So the input voltage, Vin, is higher than the desired output voltage. So we have a source, let's say a battery. It has a voltage, Vin, and you have a load, which we'll model as a resistance R, and that would like to have a voltage of V out across it. And we'll for our examples here, we'll take I'm actually make this 10 volts, and this will be 5 volts. 12 and 5 is a little hard to use. Okay, so one way you could get 5 volts across this output from a 10 volt source is using a resistor divider. And this is kind of something we talked about a little bit in the first session. So if you go ahead and just connect these guys with another resistor of equal resistance R, in this case, just because of the ratio I picked. This gives you an equation like, and how this is derived is left as an exercise to the reader from understanding session 1. Let's give these names. This is the load resistance. This is the series resistance. V out equals V in times RL over RL plus RS. This is kind of fairly basic from introductory circuits. So when I set RS equal to RL, you get R over 2R. So V in, you get V out equals half V in, which is what we're looking for, right? Okay, so what are some drawbacks to this? Did I already say? Yes, I didn't. All right, some drawbacks here are when you make this circuit, you have to choose RS, and RS needs to be somehow proportional to RL to make it work out. So if the load resistance is constant, you might be able to make this work. If it's not, you might have to be doing something tricky here to change this. But so what could we do? A controllable resistance. You could say, all right, well, I'm free to control this resistance. You make it into a potentiometer, and you hook up a little motor to turn the knob on the potentiometer, and that's controlled off of, some feedback about what the current is out here, or IL. Okay, so you can overcome the problem of a resistor divider just being kind of a fixed thing. The problem remains that, so you have a 10 volt input and 5 volt output. Where are the other 5 volts? They are across this resistor. So when you go around the circuit, you see 10 volts and then -5, -5. Everything comes out to 0 as it should. So what you end up with is the power loss in your converter is equal to that 5 volts over the resistance. So 5 volts squared over the resistance. So that 25 volts, if this load current was 1 amp, we know that 5 volts over 1 amp equals 5 ohms from Ohm's law before. So RL equals 5 ohms. We said RS had to be equal to RL. So this would be 5 ohms. So you would end up with 5 watts dissipated in your power converter for 5 watts delivered to the load. That is a pretty bad efficiency. Efficiency is defined as, what the hell is this letter? This is Greek letter eta, I think. Yeah. And it is defined as power out over power in. So power out being the load, the power delivered to the load, and power in, the power coming out of this this battery. And in this example, it's 5 watts over 10 watts, because 5 watts is delivered here, Another 5 watts is delivered here, so that all came from the battery. So 5 watts goes to the load while 10 watts were delivered by the battery. That is an efficiency of 50% and is unacceptable in most applications. So, another way we can come at this, let me see how far I went with this. Okay. A chopper circuit, and this is why we're talking about an ideal switch. Instead of this resistor, what we can do is we take our same input, we replace the resistor with an ideal switch, and our load is as it ever was. He still wants V out across it. So if I find somewhere, I'm going to erase a little bit of this, and someone will have to figure out how to calculate watts on their own. The notes later. Okay. This circuit exists in 2 states. One, when the switch is closed, the input is effectively connected right to the resistor. And the other, when the switch is open, so switch closed. And the other, when the switch is open, that the battery and load are unconnected. So if I draw that on a plot, I'm going to say V out is red here. So when the switch is closed, the voltage across the load is 10 volts. When the switch is open, the voltage across the load drops to 0 volts. And this is the essence of a chopper. You just turn the switch on and off, pulsing the load between 10 and 0 volts. If you take the average of this waveform, you're going to get some value that is in between 0 and 10 volts. And how far between depends on the on time of the switch and the off time of the switch. And let's define TS as T on plus T off. So what we end up here with is V out equals V in times, what do I say, T on over TS, which again is T on plus T off. Well, this has certain similarities to the resistor divider equation that we had earlier, so that's kind of convenient. But nowhere in this equation does the load resistance or a series resistance appear. It's just a matter of how long was the switch on, how long was the switch off. But there are definite problems with this circuit. Anyone have a guess for me? What might be a problem here?
Even when you're driving the whole time, it's not high frequency. That's what it's
Could be. It sees the 0 volts and it says, oh, there's no source there, and it shuts itself down. Could be. How about with the on time? Any problem with that? It could be with this thing designed to get 5 volts. It doesn't like 10 volts on it. Maybe some wire is only rated for 5 volts and it breaks down at 10. It's kind of unlikely at this low voltage, but it does happen at higher voltage, for higher voltage systems. So I think I wrote some of this stuff down. Okay, there we go. So some of the drawbacks were you may exceed the voltage rating of the load, and kind of what Will was getting at, pulse power to the load may give undesired results in that it may turn off. Another thing is, say it was a DC motor and you're pulsing it. So, okay, so the motor turns at twice the speed it might have at 5 volts for half the time, and then it stops when the voltage is 0. Well, from the motor's perspective, you still may get the average speed you wanted, but you're going to get it in these jerky motions, and that may not be the desired result. And there are other problems like that going on. So one of the ways we can improve that, I gave it away. So we talked about the RC filters earlier. An RC filter, or these low-pass filters. Well, that's weird. These low-pass filters essentially are averaging, in that they give you a DC value, they give you the low frequency value, while rejecting high frequency. It's going to be stuck there, isn't it? So when we talked about averaging this, seeing the average 5 volts, that is the low frequency component of this waveform. The high frequency component is all this pulsing, and that happens at, switching frequency, which we'll talk about in more detail a little later. Let's try. Hey, all right. Okay, so let's try that first. So we already had, so we know a capacitor. Damn, I'm giving it all away here in the text. So let's hide that. All right, so we were pulsing a voltage to the load, and we know, since I already gave it away, a capacitor is a device that resists a change in voltage. When a current is applied, like we said earlier. So we can redraw the circuit, battery again, our switch, and we put this capacitor right across the load. Okay, so we think, hey, this capacitor will help resist the change in voltage that we were applying by pulsing the voltage to the load. The problem with that is, again, that this switch is a perfect switch. So if you take an initial condition of this capacitor, say it's, we're just turning the circuit on for the first time. So this capacitor starts at 0 volts. Let me give him a color. Capacitor voltage starts at 0 volts. So we're going to go ahead and turn it on the first time. So the voltage applied by the switch starts at 0, and then the switch applies the 10 volts, and so on. Now the capacitor comes along. Capacitor voltage comes along, and you don't want it to jump all the way up there. But the circuit you've created with this perfect switch is that you connected the battery in parallel with the capacitor. And like we said in earlier sessions, devices connected in parallel get the same voltage. Nothing you can do about it. That's how it works. So when you apply this 10 volts from the switch, that gets applied immediately to the capacitor. It gets applied immediately to the resistor. So the capacitor has no choice but for its voltage to pop up like that. You might wonder, well, why did it do that? I thought it was supposed to resist changes in current. It does. So, or sorry, changes in voltage. So let's redraw. Let's bring this equation back up, the capacitor equation. So what we ended up here was the switch closed, and the switch closed in 0 time. So here's two things that happened. At this instant, when the switch closed, we ended up with a dV, the change in voltage was 10 volts. And dt, since the switch closes in 0 time, dt was 0 seconds. And divide any number by 0, and you will find that IC approaches infinity. So all you've done here by adding the capacitor is caused these pulses, these infinite pulses of current, which I'll draw on an imaginary second set of axes here. You'll end up with these infinite pulses of current right at the switching instant going into the capacitor, forcing its voltage up and down. Okay, so we know of a component that can resist current flow when we apply a voltage, right? And it's a resistor. So where is my cursor? So we'll we'll erase this and we'll put in our resistor with the right color. Okay, so that helps. So just intuitively, we kind of know that can help. I don't know that I should go through and draw all the waveforms right here. But what we've done is we've reformed the RC filter that we discussed in the last session. You can feel okay now when the switch closes. The effective circuit is now this kind of thing. You don't have a voltage source closed directly across your capacitor. So this resistor will have some voltage drop on it when the switch is closed, and that will drive some current. Some of it will go to the load, some of it will go to the capacitor. In essence, you'll get some reasonable, when you add the resistor, you'll get some reasonable smoothing of the output voltage. The capacitor voltage might do something like this as the switch goes on and off. So you are, again, the low-pass filter is extracting some of this low-frequency information, which is the averaging effect you want. But it's not perfect, so it does still leave some high-frequency content on there, but certainly not as much as before. So that makes the no voltage to your load problem go away to a degree. It makes the over voltage problem go away. The pulsing motor problem goes away to a degree when you do this. But the drawback comes back is kind of the same in the resistor divider circuit we did on the last slide. There's however much current is demanded by this load has to flow through this resistor on average. So that you still end up with this power loss in this resistor given as the square of the load current times, this is RS again, times the resistor. I don't have convenient numbers. I can say, oh, this resistor has to be, half an ohm or whatever it is. Suffice it to say that because you have the capacitor there doing some of the job for you, it's not quite as bad as this 50% efficiency here. But it's a good amount of power loss to especially when you get to higher currents. This efficiency of this circuit might be in the range of 70 to 75%. So that's a big drawback. So what might we do instead of a resistor there? I'll give you guys one option, or one. Yeah, that's the component you get to change. Any ideas what other component we might want to put there? That's it, which should be pretty clear if you've seen any of our schematics. So.
But you should ask why.
I should ask why. It's the only last one. But what's the property of an inductor that makes it interesting in this position? Right, it resists a change in current. While the resistor resists an absolute, resistor just resists a current flow. The inductor resists a change in current flow. And ideally, an inductor does so losslessly. So we add giving it all away. Let's just, all right, none of you saw that, so I'm just going to erase and draw my inductor in now. Okay. So let's give the inductor a color. He is going to be, no, I already have red. Oh, purple, beautiful. All right, inductor current and inductor voltage. Okay, so we put an inductor there. Let me get a new set of axes here. And we're going to look at the voltages and currents at some different places. All right, this is going to be battery, voltage, current. We'll have the inductor, and we'll have the capacitor, which will also kind of, in some ways, serve as the load. Well, maybe we'll add some axes over here for the load later. Okay, so what did we say for the battery? The battery is doing its thing, or this is, say, the switch voltage here. Okay, so it's switching between 0 and the battery voltage. That's just what it's doing. We're going to assume, let's just make the assumption for the moment that the system is operating how we want. So this is the RL, and we're getting this nice, perfect smoothing of the circuit. So we get V out equals 5 volts here. So we're going to make that assumption just to make life easy for us. All right, so that's the battery volt, the switching voltage. So that's applied right here. Given the assumption that the resistor voltage is basically fixed at 5 volts, what we end up with is a inductor voltage that, if you take 0 minus 5, you get minus 5 across the inductor. When the switch goes on, you get 10 minus 5. So the inductor voltage goes positive. The scale is a little off here, but forgive me. Okay, so the inductor voltage is going positive and negative. If we recall the inductor characteristic equation, VL equals L DIL dt. So a negative voltage applied to an inductor is going to give you a negative change in current. I'm going to draw it up here for reasons that I'll expand on later. So inductor current is changing at a constant rate, negative, while the switch is off. When the switch turns on, the voltage across the inductor changes instantaneously from -5 to +5. Now the current is increasing. It's increasing with the same rate that it was decreasing before. Give me a break. And this just goes on and on. Okay, so the inductor gets that current. Great. Now we can move on to the capacitor. So we said we assume that the circuit is doing a good job. So that the output voltage is equal to the desired 5 volts. So since the capacitor is in parallel with the resistor and voltage across parallel components is the same, the capacitor also gets this nice 5-volt output. This is an approximation. It's not going to be exactly this way, but it's useful for the analysis. Okay, so good. And the resistor, we know by the equation for a resistor, once we have a voltage and we have a resistance, and those two things are fixed, then the current through the resistor is constant. So good. The resistor is going to have a constant current through it, since the voltage across it is constant. So I have into this node here, you have inductor current coming in, you have load current going out, and capacitor current going out. So if I would state that in equation form, IC equals IL minus, I've got 2_L. And I've just made my language slightly inappropriate for putting this on the internet. The inductor current minus the load current is the capacitor current. If we just do this graphically, what we see is that the capacitor current ends up just with this. He ends up with the triangle current, the triangle wave current that's in the inductor, but now it's centered around 0. That was the thing I glossed over here. I drew this inductor current up here above 0 because I knew the average value of the inductor current had to go to the load. By the same reasoning before that we said the load current had to flow through the series resistance, the load current must flow through on average, flow through the inductor because that's where the source is. The source is behind the inductor, so it has to flow through there. But hold on. So we have these basic equations, but what is the problem with this graph? If we look at the circuit when the switch is closed, we have the battery, inductor, capacitor, resistor, right? Okay, so this all makes sense. You can have a voltage across the inductor, a voltage across the load, and current flowing through the inductor, current flowing through the load, current flowing through the capacitor. When you turn the circuit off, when you turn the switch off, the circuit goes to battery. The battery is disconnected from the circuit. the inductor and capacitor and load. So there's definitely a current flowing to the load. And we said here that there is a current flowing in the inductor. Can that be true? The answer is no, I guess, or else I wouldn't have asked it. Because there's no way for the circuit to be completed, because you disconnected the battery from the input. So this really can't happen. If you tried to do this in a real circuit, you built up some current in the inductor and turned the switch off, this current would have nowhere to go. So the current would have to stop instantaneously. And by just the same thing we did over here with the capacitor, doesn't matter what the change in current is, if you make that change instantaneously, you end up with infinity on the left side of the equation. So if you try to switch an inductor and you don't give that current anywhere to go, the voltage across the inductor will spike to infinity and probably blow something. In this case, it's an ideal switch, so everything's fine. It's an ideal switch, it's an ideal inductor, so nothing breaks down. But in real life, that doesn't happen. Wires break down, air breaks down with an infinite voltage. So I drew over yes. I do believe I meant to do all these on the next slide, but you've already had the benefit of it. So what we end up doing is we add, so this is the switch we showed earlier, and we end up adding a second switch so that the current in the inductor has somewhere to go when the top switch is off. So if we look at the switch waveforms, we're going to call this the top and bottom. Make this guy red. So the top switch turns on and off, doing the the top switch is doing the chopping work that we've been discussing this whole time. The bottom switch, all it needs to do is be on when the top switch is off to allow current to flow in the inductor. So the two switch signals end up complementary of each other. They're exactly opposite. When the top switch is on, the bottom switch is off. When the bottom switch is on, the top switch is off. So let's draw out the circuits. Top on, bottom off. You end up with the voltage source connected to the inductor, the capacitor, and the resistor. Sorry, you'll note this is the European resistor symbol over here. The simulation program, Plex, is developed by Swiss people, so they use the European symbol. Okay, so this circuit looks fine, valid. The inductor can complete a circuit. There's no voltage source attached to the capacitor. Great. If we look at top off and bottom on, we end up with the voltage source disconnected and the bottom switch connects the inductor, back to this bottom wire. And this works too. The inductor has somewhere for its current to flow. And again, nothing unseemly is connected across the capacitor with load. Let's look at the other two situations we can have. We can have top off and bottom off, which will give us essentially what we saw on the last page, where the battery is disconnected and so too is the inductor. So this was the problem from the last page. And if we look at top on and bottom on, we get this. This looks okay for the inductor. He's got somewhere for his current to flow. The problem comes with the battery. Now the battery is just short-circuited to itself. And again, these are ideal switches with zero resistance, and this is a voltage. So voltage over zero is going to give, a fixed voltage over zero resistance is going to give infinite current. And so this is not a valid state. So this is not a valid state because of the inductor not being allowed to complete a circuit. This is not a valid state because of the battery or the whatever the input source voltage is being shorted and driving very large currents. So these are the only two valid states, and that's how I ended up here. Top on, bottom off, and top off, bottom on. And this is basically the kernel of all of the power converters we do here. That you have a top and a bottom switch, you have an LC filter, and you have a load. There may be other components connected, there may be current sensors, there may be EMI filters, but this is really what it comes down to. You can have multiples of these for three-phase converters, you can chain these in series, you can put them back to back, but it really all comes down to this basic thing that
You haven't mentioned efficiency.
Oh, I haven't mentioned efficiency of this one. No, you're right. That's a good idea. So we said earlier that RL is, we know that there's about 5 watts dissipated in this load and 5 volts across it, 1 amp through it. And this is 10 volts. I'll actually have to go back a slide to go through this completely. And ideally, what I said was that the switches are ideal, that they are ideal, that the inductor and capacitor are ideal. So these are all lossless components. So I don't have to accumulate any losses for those. So the power delivered by the battery is just 5 watts. So when we look at efficiency, 5 watts over 5 watts is 100% efficient. All of the power extracted from the input is delivered to the output. Now again, nothing's ideal, but that is the draw of a switched power converter versus any other, versus any lossy linear. They're called linear regulators, that resistor divider we showed earlier. Let's take a step back and talk about the battery, the input a little more. So I left this guy blank, right? So when you end up here, so the battery voltage, the battery current when the switch is off, the battery is disconnected from the circuit, so his current is 0 when the switch is off. When the switch is on, the battery is in series with the inductor, and components in series always have the same current, just like components in parallel always have the same voltage. So we just look at the inductor current over here and say, all right, battery current equals inductor current when the switch is on. When the switch is off, and it goes back to 0. So if you end up looking at the average of this current, it's, you sort of know the average of the inductor current was equal to the load current, which we said was 1 amp. So you now have this pulsing waveform that is, let's say it's about 1 amp. 1 amp would be right here. You know, it's a trapezoid, it kind of works out. I'll spare you that math. So you end up with these 1 amp pulses, and you take the average of a 1 amp pulse, you end up with about half an amp. Since this is all, you know, a 2-to-1 ratio here. So the battery current is reduced. So here, let's say this another way. We already defined earlier that the output voltage is equal to the input voltage times the on time over on time plus off time. What we can say from this plot is that the input current is equal to the output current times this same factor, T on over T on plus T off. So with this circuit, the output voltage is lower than the input voltage, and the input current is lower than the output current. And that's why, you know, that's how we got, you can look at it here too. You assume the efficiency of the circuit is 100%. You pull 5 watts out of the 10-volt battery, that gives you half an amp. You end up with the same result if you come at it from that angle as well. So let's talk a little more about this part of the equation. Because everything I did here assumed the input was twice the output, and that made certain things happen. What did I say here? Okay. So I've been saying that part of the equation is T on over T on plus T off. We will define that as a duty cycle D. And that applies to the top switch. So when we had 10 volts in and we wanted 5 volts out, remember V in equals now D times, with this definition you get V out equals V in times D. Since we wanted 5 volts on the output and 10 volts on the input, you end up with 10 over 5 equals D equals 0.5 equals 50% duty. Is what we ended up with there. Okay. The complement to the top side duty cycle D would be T off, T on plus T off. This would be the duty cycle of the bottom switch, and we define that as D prime. And for the purposes of this company, we will always define the top switch duty cycle as D, and the bottom switch duty cycle as D prime. If you look up certain converters on the internet, you will see this switched. You're not doing that. Top switch is always D. Okay. Let's talk. We'll get to the reference carrier. So if we had different requirements, say we had a 12 volt in and we still wanted our 5 volt out. Take 5 divided by 12. That's going to come out to some number less than 50%. Because we know how to do that. Why didn't I pick 15 volts? And I would have made life easier for myself. 5 volts divided by 15 is something I can calculate. You need a 33% duty cycle to make that happen. Or maybe I wanted a 10 volt input and an 8 volt output. So 8 divided by 10 would be an 80% duty cycle. The degenerate cases here are 100% duty cycle is just leaving the top switch on. And it's just the same as connecting your input to your output. So your output voltage will be your input voltage. The other case is a duty cycle of 0, where you're just leaving the bottom switch on. And that will just result in your output voltage being 0. So those are kind of the intuitive end cases you can think of to justify this to yourself. Sure. I didn't really give myself a lot of room to talk about this, but one way to generate the pulse train that gives you your 50% duty cycle or your 33% duty cycle or your 80% duty cycle. One way to do that is a circuit called I don't know what it's called, actually. It's just a pulse width modulation circuit. That's what, when we talk about changing duty cycle in order to affect these changes of input, I guess step back a second. Why I talked about these things here. You can change your duty cycle to compensate for a change in input voltage. And you can change your duty cycle when you want to change your output voltage. And that changing is called modulation. You're modulating the pulse width to get the desired relationship between the input and the output. So a common PWM circuit is, what is it? Is a comparator. And the comparator really just implements a greater than function. If V plus is greater than V minus, this thing outputs 1. And when it's less than minus, it outputs 0. So into the minus, you end up feeding a triangle wave. Into the plus, you end up feeding your desired duty cycle D. So let's draw that out over here. Getting better at that. So D ranges from 0 to 1, which represents 0 to 100%. So your triangle wave is also going to go from 0 to 100. So say I want my 80% duty cycle. I'll put that right here, 0.8. I feed that into this comparator circuit. So during this time here, D, which is V plus, is greater than what is called the carrier. The triangle wave is called the carrier. Let's write this in here. D is the reference. The triangle wave is the carrier. So the reference is greater than the carrier, so the output is positive, is 1. And that would be controlling this top switch, remember. In this second time period, the carrier is greater than the reference, so the output goes to 0. In this time section again, the reference is greater than the carrier. So the output comes up, and if I was better at drawing, it would have happened right here. And this just continues on. So you can see, roughly, not to scale, that by having the reference up here at 80%, you get this 80% duty cycle, where the on pulse should be 80% of the total time here. That's generating PWM in a very simple way. Depending on circuit conditions, you could be changing this reference continuously. Say your input voltage was a battery that was charging and discharging, due to some external circuit. You could modulate this reference in order to maintain your 5-volt output. Or, if for some reason you had a reason to do so, you could raise the voltage on this resistor. Maybe it's a voltage-controlled motor, and you want to speed it up. So you can raise or lower the reference in order to raise or lower the duty cycle, which would then raise or lower all of that, respectively, the output voltage. So this is that's very important to what we do. All of our controlling a power converter really comes down to changing the reference into this pulse width modulator in order to affect a change in the switching pattern, in order to affect a change in the the output circuit voltage. And that is basically an ideal, what I'm calling here, I didn't say this word once, even though I wrote it. This is an ideal buck converter. And that's basically what you need to know about it for ideal components. We didn't talk about, the things we didn't talk about here are what should this switching time be? Call this TS. I think I did that earlier. What should that be? And correspondingly, Fs is 1 over Ts. What should the switching frequency be? And why would you care what the switching frequency is? I didn't talk about choosing the values for L and C. Those go together with the switching frequency. That's all, that's all stuff that is part of the detailed design of a power converter, but it's not really necessary to understand the basic concept. And everything else I'm not even going to mention because you don't know that it's a problem for you yet, so it's okay. And that is it. So let's, I think I like the way we ended this last time. Let's come around the room and everyone, just tell me one thing you learned from this experience. I expect there are a lot of things that each of you have picked up on this particular one, but let's hear it starting with Preston.
I like hearing about the parents want to do it with the inductor.
Right. Yeah. This. I get it. This invalid state. Right. And there are some. We'll get into it in the next session about how, in some cases, you can get this effect without having a controlled switch here. But it depends on different devices than the ideal switch. The ideal switch can't do it. So we'll talk about that next time. Stephen, I guess you have some electrical background. What is your main takeaway?
I don't have an electrical background, but main takeaway is that circuit right here. That's what we use it here.
Yeah. Yeah, basically everything is made up of this guy, or a number of these guys. And there are ways to control them. There are ways to control this circuit that don't look like this, this chopper circuit that we sort of started the session off with. But we don't use them here. And these are by far, this pulse width modulated fixed frequency converter that we've been talking about is by far the most common in industry. Vinay.
It's a pretty good refresher, but
yeah. That's good. Yes, you should have had this. Yeah. How about it, Ani?
I'll tell you, from basic circuits, it shows like justification why diagram, something level out.
Right. That's good. Yeah, I was trying to lead you to the conclusions, and then beat you over the head with it, if I could. Ryan?
Same thing with Lonnie, really made 4.3 much clearer.
Which is the power electronics class at NC State. So, all right, take that, Alex Wong.
Yeah, well, actually, classes.
This is going on the internet, just so you know.
But I guess overall, I really thought about the preference of the period, how I should bring it.
Great. And on the carrier, I made a choice here. I drew a symmetric triangle wave. This can be done with like a sawtooth pattern as well. This is better for reasons I would not even be able to hope to get into until many sessions later. But know that this is the one to use, what I call a symmetric triangle wave rather than a sawtooth. Hey, what?
I was going to say that's something I've seen Preston modeling PW over the head, I think exactly how or what he was doing, all of his favorite things.
Yeah, and there are some details about how we're doing it, how we have to implement it in the FPGA for dealing with variable switching frequency. Just for implementation's sake, we end up with some things where, well, the duty cycle is not really between 0 and 1. It's between 0 and some 2 to the n, where n is the number of bits in a digital system. And the triangle wave has to be scaled for the switching frequency and all that, but this is basically what it's trying to recreate. All right, Jeremy, you learned nothing here, right?
One learned, so I was really questioning why you went straight to 2 switches instead of model switches of 9. I think it actually worked out quite confusing. But I was like, why didn't we do the math? And I think it actually worked out.
Yeah.
Because it leads to what happens in the real problems.
Right.
Dies.
Yeah, the dot.
Yeah. This is going to be better in tears. Nobody's going to know why this happened. It actually worked out. Assuming everybody else got it, which I think they did. I liked it.
Yeah. So we'll. The importance of the diode for this type of product comes in, especially when we start having non-ideal switches, which by the way is the next session to talk about switches that don't work in infinite time and don't block voltage both ways and don't conduct current in both ways, and how we have to deal with that.
And that makes sense. And the only thing I've seen people talk about putting in the mouth of the diode.
Right.
Which you just skip.
Yes.
Switch straight to probably the middle of it. I like it.
Adam?
Overall, it's just interesting to see. I get to see a basic power converter. I'm with Will and Ryan. It's interesting to see how you can modulate the duty cycle using those derivatives superior.
Okay, great. Well, so like I said, next thing will be we'll talk about diodes. We'll talk about transistors in place of these ideal switches. And some of this discussion will lead to why do we care about silicon carbide, which seems to appear in every second or third project we do, and we make such a big deal about it and honestly make a bit of money on it. So we'll talk about why that matters at all next session. I didn't put session numbers on these yet because I bet some of the stuff will get stretched out, but I want us eventually to talk about alternating current, AC power. Basically what we reviewed today is best thought of as a DC-DC converter. You have a DC voltage input, you put a DC voltage output. Even if you're changing it over time, it's still basically DC because it's missing some key features that are required for AC power. So we'll talk about AC power first, and then after that, we will talk about using a number of these buck converters we talked about today in order to create AC power, and how we can sort of modify that. And then going, further down the line, we'll, as a company, we do energy storage integration, we do power converter control, we work with generators, and we want to talk about all of those things at some point, at least at a high level. So that's what we got. All right, I will stop here. Oops. Well, I'll stop the recording because I've already stopped the screen share, if I can figure out how to use my computer. All right, thanks everyone, and talk to you next time.